Hey there, this is a video I've been meaning to make for some time, ever since we started talking about curve fitting and regressions, probably more than a year ago. What I want to do in this video is to take a look at a very complicated problem where we're going to come up with a physics-based model based on some research paper of a battery, and pretend we have some experimental data and we wish to pull out some parameters that go into this model from our experimental data. Now, the issues here are going to be several. Even though the model is comparatively simple, there's still a lot of differential equations, a handful of differential equations, a bunch of algebraic equations, and then cases where we have to do some sort of spline interpolation to get various values that go into the model. So the actual model code itself is relatively complicated compared to things we've done previously. But the main issue is the parameters that we're going to try to pull out of this model vary by 10 to 15 orders of magnitude. So that will cause problems with your fitting routine, and we're just going to use the SciPy curve fit function, but you could use minimize and build your own type of least squares routine if you really want to. But I'm basically just going to show a couple tricks to deal with the cases where these parameters vary significantly. So with that, let's just jump into a notebook and get going. So this is the paper I'm going to base this simplified model on. The typical way you would model a cell in terms of physics is each electrode is comprised of maybe 100 or so different particles. And the lithium, the ions move in those particles in a diffusive manner. So for every particle, you'd have to solve a diffusion equation. So what this model does to simplify that is basically just consider these all as one huge single particle here. Hence the name, this is often referred to as the single particle model for that reason. So we go from maybe hundreds, 200, 300 or so diffusion equations down to just two, which speeds things up, of course, tremendously. But this paper goes a step further and tries to come up with an approximation, an algebraic, an ordinary differential equation to approximate the lithium concentration in each of these particles. So we're not going to go through the derivation. It's not even entirely done in this paper, but you know the boundary conditions are related to the ion flux, which is related to the current, and there's a bunch of other coupling equations. So let us go over to a notebook and let's look at what we are going to deal with here. So let's shrink this down. So these are our differential equations that we're going to use to approximate the diffusion equation. So this x bar is basically a fractional percentage or an average percent of lithium in the electrode. The p here, I don't know if you could see it in the video, but the p stands for the positive electrode. This n stands for the negative electrode. So we have a differential equation that covers the positive one, the cathode, and a differential equation that covers the anode, the negative electrode. So you also have a couple of algebraic equations which relate this, you know, the average lithium concentration to the lithium concentration at the surface of the particle. That's what this notation means. At little r, the radius is equal to 1. So we're assuming the particle only has radius of 1. So this is the concentration at the surface. These J's refer to ion fluxes, essentially. So you have two algebraic constraints on these differential equations. Now, the particle flux is related to the overpotential by these essentially Butler-Volmer type of equations. They're very nonlinear. You can see the exponentials. The S's here refer to electroactive surface area, and they're related to the applied current. The I is the current, and the particle flux is by, excuse me, by this relation. The relationship between the phi is the electrode potential and the overpotential, they're related this way, where U is the open circuit potential. You can think of U, if you come back to this schematic, as the voltage of each individual electrode as a function of its lithium concentration, assuming there's no current or anything being applied. So as the concentration of lithium changes, the voltage of each of these electrodes will change. And that is what that U is there. And then lastly, the cell voltage is just the difference between the two electrode voltages. Now, one of the problems we have is these open circuit voltages for each electrode are generally measured from half cell measurements, and we don't have an equation for this. I've basically made up some data here to describe that and plotted them out. So you do a measurement and you just get, a bunch of dots. So not only do we have a whole bunch of nasty equations to worry about in our fitting routines, but we also have to do some sort of cubic spline interpolation to get these open circuit voltages. So what we're going to do is assume we have a discharge curve that we've measured. We've taken this cell, we've discharged it and got a bunch of voltage points as a function of time. And the problem we're going to look at is we want to know what this diffusion constant for the cathode is, this dP, as well as the the electroactive surface area, SP and SN for both electrodes. So we need to pull out a dP. Where's our dP here? Here from this equation. We want to basically do a curve fit to estimate this dP and these S sub P and S sub N. And a further complication is these S's, whereas these S's here are typically of order 1 to 10 to 15, so they're about, let's just say they're in the order of 10. And these diffusion constants here, dP and dN, can be on the order of 10 to the minus 10 to 10 to the minus 15. So there's a huge span of potential values that can screw up our fitting routine. So let's come down here and think about how we might address this. Now the code for this is going to get kind of complicated because we have to code up all of this and pass in a bunch of these additional constants like the particle radius and so on, rate reaction formulas, rate reaction values, which are these K's down here. So obviously I already did the imports here. Because this is going to be a differential algebraic equation system, we're going to use the sundials package, the Simula package, which is based on the sundials library. We're going to use the curve fit from SciPy Optimize, just so that we don't have to code up the sum of the squares part ourselves. We'll just use the curve fit function to get around that. And of course, we're going to need the cubic spline and plotting libraries. So the way I'm going to basically do this is just put everything into like one big class. It's kind of clunky and ugly, but it'll just, I think it'll be easier to follow. So I'm going to create a class called battery model. We define our constructor. We're not going to have the constructor take any arguments. So what I'm going to do now is copy and paste a bunch of these values like the K's and the radii and stuff, just so we don't have to type it all out by hand on the video. So okay, here are the values we're going to use. The CP max for the cathode and anode is the maximum lithium concentration based on the stoichiometry. Our P is the radius of the cathode, our N radius of the anode. CE is the electrolyte concentration. We're just going to assume that it's a constant. It's a simplification of the model. Otherwise, you have to do a diffusion equation as lithium diffuses into the electrolytes. F is the Faraday constant. R is the ideal gas constant, and Dn is the diffusion constant for the anode. And the reason I'm not going to fit this, or originally when I planned out this video, I was going to fit this as well, but it turns out it's not very sensitive to that, so it just kind of gives kind of quasi-random values for this. So I just wanted to just hard-code it in here. These are the initial initial lithium concentration at each of the electrodes, cathode and anode respectively. I don't know if we're going to use them, but I copied them in anyways. And we're going to use a current of 15 amps for the discharge. And because we can't let this go out of bounds, we're going to set a lower voltage cutoff of 2.5 volts and pass that into our differential equation solver for it to end the simulation if the voltage gets down to 2.5 volts. So I'm going to create OCPP data, which is going to be our open circuit voltage data from these plots here. So this will be the cathode and anode. Maybe I can just copy this in. I'm going to copy, paste. So we're pulling in our data files, and now we need to create cubic splines for these files. Okay, so right now I'm going to code up all those differential equations, and I'm probably going to edit this down for time because there are like a dozen equations. I'm going to call this function res. If I don't do any editing, it will be here forever. Remember, our function takes the time variable, our vector of algebraic variables, which we'll call x, our differential variables, which we call x prime, and this variable called SW or switch, which is not used in this problem. So let's begin to code up. Let's see, where are they? These first equations, these first four equations here. So what I like to do, just to keep the bookkeeping and code base cleaner, is to pull out all these variables into their own, defined arguments, like x sub p. The average concentration in the cathode will be x0 and so on. So we have 11 variables here, and I'm not going to do the same thing for the differential variables just because there are only two of them. So we'll just live with that. So what I'm also going to do is I'm going to pull out these variables, which are going to we're going to end up using to fit our equation from the class variables. Just again, it'll help keep the code a little cleaner. So dp s sub p is equal to self dot s sub p, and likewise for s sub n. So okay, here are our particle fluxes. I probably should have made these like variables just as I did the others, but I didn't, so I don't think it'll be a big problem. So here are our first four equations that correspond to these up here. So this is our first equation here, this would be our second, this would be our third, this would be our fourth, and so on. And I don't think I usually like to predefine these vectors that we're going to return. So I'm going to say res is equal to np dot zeros. I just think it's a useful thing to do. Keeps the code cleaner a little bit, and it's probably just a leftover from my C coding days, but I like to allocate the memory ahead of time before putting things into the array. So the next two equations correspond to our Butler-Volmer equations. They're pretty straightforward. One thing I forgot to do when putting in all these class variables was put in the numbers for the k's, k sub p, k sub n, and the cell temperature. So I did these up here, k sub p, k sub n. The cell temperature is 298 Kelvin, 25 degrees Celsius, and those would correspond to these two equations here. So our next equations deal with the open circuit potential. So the open circuit potential U sub p this is where we use our cubic spline interpolations to pull out a value. So essentially U sub p is equal to our spline interpolation, pretty straightforward. So I fixed a typo, and I need to create our guesses for our initial conditions. Remember, differential algebraic equations, we typically don't know all the initial conditions, we have to solve for them. So I'm going to start this as np.zeros, and we have 11 equations. And now I'm just going to basically list these out. So here we are. We're going to assume that most of these values are 0. The cell voltage here, which is our last variable, typically is between, say, 3 to 4, so we're going to guess 4. And these lithium concentrations, we're just going to set them equal to the numbers that we set above. So x1 and x2 might slightly vary from each other. One's, remember, a surface concentration, one's kind of an average internal concentration, but that's what we'll use for our initial guesses. So now we need to come down here and do the same thing for the derivatives. So here are the derivatives. I need a closing parenthesis. We're just going to assume that they're all 0. We need to pass an initial time to the solver. I'm just going to hard code it to be 0 seconds. And in case we do not pass in a list of times where we want our solution, I'm going to create a variable called tspan and set it equal to 4,000 seconds. So a little more than an hour, just to test things out if we don't pass in anything specific for our time steps. Okay, so we define the switch variable, which we don't need. We need to pass it in, but it's not going to be used in this code, so we set it all to falses. The algebraic variables, the first equation and the third equation are differentials, and everything else is is algebraic. Let's just see how many typos there are at this point. Looks like I have a period instead of a comma in the function definition here. I have a habit of doing that recently, forgetting the equal signs. So we create our model object here. We're going to bind some event functions to it, which we haven't written yet. We create our simulation object based on the model, and then of course attach our algebraic variables to that. So let's define the event function actually before we go on from here. So here's our event detection routine. The last element in our x vector is the cell voltage. And we're ending the simulation if that reaches some sort of cutoff. So whenever the voltage is equal to the cutoff, this term is 0. It triggers this function. It looks to get its instructions here, which is just end the simulation, and that is that. So let us come back down here and put in the last few lines of this function here. Okay, so we calculate our initial conditions, and based on whether we're passing in a list of times, we either call this function call the simulation function with like 100 data points evenly spaced, or we pass in our specific list of times, and we attach the results to the class variable v. So what I want to do now is just test this to make sure we can actually run this code just by trying to do a simple discharge. So let's just create a variable called model, and that'll be equal to battery model. Let's just see if that actually runs. It does, and now we should be able to call model.run simulation. Let's pass in a value of 10 to the minus 13 for D. I don't know, 9 for the cathode and 8 for the anode. What did I do here? I must have deleted the no attribute XP. Here it is. Self.xp, self.xn. Why are my indentations all weird here? That looks okay. So when this happens, there's a problem in the simulation itself, and we can backtrack to this, which gives the sundial's error, and it looks like the variable t cell is not defined. So let's go and make sure that we have that set up properly. So here I forgot to put self. Likewise down here, self. Run. So far so good. Let's just plot this to make sure we are getting reasonable results. plt.plot model.t model.v, and we'll make it a black line. Excellent. Looks good. Cutoff happens at 2.5 volts as we thought. Okay, well, now let's go on to the curve fitting part. So I'm going to come up here and create a function, and I'm just going to call it objective. Self, and it's just going to contain the arguments we've been talking about, dp, s sub p, s sub n, and it's basically just going to run the model that we just had. And I'm coding this in a way that shouldn't work. I probably should have tested this beforehand. I don't think it's going to work, and that is intentional. Because these parameters vary over many orders of magnitude. I mean, at least 10 to the 12, 10 to the 13 type of thing. So let us just pull the voltage out from that solution vector. And now I think I deleted. Yeah, I already deleted the plot. But you can have cases where, because of the parameters, the cutoff is before the time in our experimental data, so we may end up with fewer points than we expect. So what I'm going to do is add an if statement, and then if the data point has, if our simulation has fewer time steps than our experimental data, I'm just going to pad the result with like zeros. So if t dot size is, something seems off here. T, there should be a t here, the time steps that we're passing in from our experimental data. So if those are different in length, if the number of voltage points is less than that, so we've truncated our simulation before we reach this final time, we're just going to create a vector of zeros and pad our answer v like so, and then we just return v. See if that runs. Excellent. And now let's just create a function called doFit. Self. We need our experimental data. Okay. I need to create a vector of initial conditions, so I'm going to guess the diffusion constant is 10 to the minus 13. The cathode surface area is 10 square meters, and the anode is likewise 10 square meters. So now all we have to do is call the curve fit function. So here we are. Here's our solution, our optimized parameters. I also have it output the covariance. Curve fit, our function is objective. Data, the x data, our time steps, our experimental time steps, our experimental voltages, and our initial guesses. So just to see if this works, I'm going to print p, and eventually I'll return it, but let's just test this now. First, let's plot out our experimental data so we can overlay our simulated curve on it eventually. So data is equal to np.load text, experimental data, plt.plot, data, column 0, data, column 1, and we'll just use, what will we use? We'll just put points. So that's what our experimental data looks like. And now let's just run the fit down here. So I want to say model is equal to battery model. Make sure that runs. It does. So now we'll just call model.doFit. Does not have, did I not run this cell? Run. I think the problem was actually with indentation, so let's see if this runs now. Okay, so I fixed a whole series of typos. This should have been a P0 here. This was not centered properly. There was an extra indentation, a couple other minor things. So let's just run this and run this. So as you can see, and I have edited out this, this was like 5 minutes, and you see that this optimization has failed. So we haven't even been able to get a single number out of here. And of course the issue is that the parameters differ so wildly in size. So ideally they'll be on the same order of magnitude, and there are a whole bunch of different ways to do this, but since we've already written a bunch of code, one simple way, instead of fitting the actual parameters, we will fit the log of the parameters, so log base 10. So our initial guesses, instead of 10 to the minus 13, it's just going to be 13. 10 to the S sub p is not 10, so log of 10 is 1. Likewise, log of 10 is 1. So we're passing in these numbers, and in our simulation up here, we're going to have to rescale these parameters. So let's say d underscore p is equal to 10 to the d sub p. S sub p is equal to 10 S sub p, and S sub n is equal to 10 S sub n. Hopefully that works. Let's try it now. Run. I see it doesn't like integers being passed in. So where? Let's make our initial guesses 13.0, 1.0, 1.0. So it looks like we have a successful optimization. So let's just come back up here. We will get rid of this print statement. We'll keep that in the print statement, and we will just return P. Run. And now let's use those parameters. Remember, we have to exponentiate them. We will run a model. So let us go down here. And we'll do P is equal to that. We will do what? We will do, let's do dP is equal to P0, and we need to exponentiate this, so it's 10 to the P0. S sub P is equal to 10 P1, S sub N, 10 to the P2. And now let's just call model.run simulation. Model.run simulation dP, S sub P, S sub N. Does this run? It seems to. Let's just double check that and slide this thing all the way down. And let's plot out the simulated model here. So plot model.t, model.v, and we will make this a black line. Typo, of course. P2. Boom, looks like we nailed it. So with quite a simple change to the code, we were able to actually fit it. I played around with this a bit off of the recording, and without doing this trick with the logs, you had to pretty much nail the conditions initially. And you'll notice that where is our value of dP? Let's just come down here and print it out. dP, capital D. It's something on the order of 10 to the minus 11, and up here we put an initial guess like a factor of 100 different. Where is it? So 10 to the minus 13. So yeah, that's a lot more robust. Cool. As I said before, this is something I've been meaning to do for probably about a year now. Complicated parameter extractions, fitting a complicated system of differential equations to some experimental data. And when these parameters vary over many orders of magnitude, you need to find a way to rescale them so they're roughly on the same order. We just took the log in this case. You could do various things, various transformations of variables. I just did this, the first thing that came to mind when I saw this problem years ago. So as usual, I will clean up the notebook, make sure all the code works properly, upload it to GitHub, and until next time, I will see you.